So hey, person joining in, we're talking about Laplace transforms today. There's on the left what a transform is in general, and they're linear. Here is the Laplace transform kernel. You're mostly caught up. And you missed a lot of stuff I didn't want on tape anyway, so this is good. Okay, so it uses this. So in other words, the Laplace transform, now we're going to move to a fancy L, the Laplace transform of a function is defined to be, let's fix this up. Let's actually make this piecewise. So e to the negative st when t is greater than or equal to 0, and 0 otherwise. So this function looks something like this. If this is t, and this is e to the negative st, or this is just k, I've always said it's k of st here. It's dead over here, so it's just completely 0 to the left here. And then it kicks up to this. Notice when t equals 0, that spits out a 1. So it's just 1, and then it goes like that. We're going to always pretty much assume s is a positive number. That doesn't touch the axis like it looks like, it's asymptotic. That's half-asymptotic. That's half-asymptotic. I like that. That's my new thing. Okay. So when I put this in, it kills off everything to the left of 0. So you don't need anything where t is negative. You can start right at 0. And now when t is positive, or 0, I've just got e to the negative st f of t dt. And this is what you need to know for the Laplace transform. That's our formula. We'll have different conditions on s that make this true, but in general, s is going to be positive. Sometimes it can be negative, but we'll fix it all up. So let's do some examples. Now, I got to tell you, you're not going to know why we're doing this for a while. It's going to take a little bit of time to see the method to the madness. I'm hoping that today you can maybe see a little of the method, but we're going to do a little development right up front. This is going to help us solve diffie-qs in a very different way. So let's do some basic computations. What's the Laplace transform of 1? Well, let's go through. So e to the negative st times 1 dt, that's pretty happy. Maybe I should just give you a minute and see what you do with that. How's that integral work for you? Just take a moment. We'll come back together. Let's take 90 seconds. My pen lid, so I don't know. I guess this pen's going to be dead real soon. In proper calculus, you would replace that upper limit with a b. And put a limit out in front, just to be careful. Just put some sanity checks up there if you want. What is the final answer? What will you think? What did you say, Lavina? 1 over s? Yeah, that sounds right to me. Yeah. Let's finish this up. And we'll talk about that s in a minute, but that's exactly the right answer. So this is better for safety. You can, if you want, you can put in infinity up there, just keeping in mind that that's sloppy and informal. But as long as you know what it means, it'll be okay. So let's put the b in. I'm going to stick with my limit thing for a minute. Put the b in for t. Remember, this is t equals those two things. So e to the negative sb. And then when I subtract and put in 0, I just get plus 1 over s, because e to the 0 is 1. When I put that in, and then minus minus. You see it okay? Now, here, this thing here, we're taking the limit as b goes to infinity. So I want this to essentially be this 1 over e to the sb, where everything is positive here, where this is a positive multiple of b, because then this will go to 0. But if I have this as a positive exponent that's getting bigger and bigger, things are not good. This will not converge, and it'll go to negative infinity. So what we need here, for this to go to 0, is that s has to be a positive number. So we get a little condition that the Laplace transform of 1 is 1 over s, and we just make a little side note that s has to be positive. We're going to do some really cool stuff today. Is there any questions on that, my friends? You might not even quite know about it. Questions will build, right? Like the unease will accrue, possibly. Let's do the Laplace transform of t and see something really cool. And then let's start abusing notation. So I put the t here, dt. How do you do that integral? What Calc 2 technique? It's so quiet. It's still very yes, yes, so very good. You said, yes. Yes, use substitution would definitely be helpful, but I also have this product of two things in here, right? Like just that we can do, but what do you do when you have a product of things?
UDV thingy.
UDV, you get parts. Yeah, so we need to use parts on this. So use parts. And substitution along the way if we wanted. So here I'm going to let u equal t, because that will become simpler when I differentiate. I'm going to let dv be e to the negative st, because it's not the other part. And it's actually not too hard to integrate. In fact, we just freaking did it. Then we go to, remember the form? It was integral udv equals uv minus integral v du. That's the form we're going for. So this is going to equal u times v, so negative 1 over st e to the negative st, and now here's where I get abusive. 0 to infinity. I'm just going to pretend like infinity is a place, but I'm going to keep in mind that's a limit I'm taking. And then minus becomes a plus, bless you. Notice the 1 over s is a constant with respect to our variable t. So I've got 1 over s integral 0 to infinity of e to the negative st. I'm going to secretly put a 1 in there just to like see if I can jog any noticings of similarities. That'll look nice. They'll tell me if that looks reasonable.
Is that like integral or like the sign?
This here? Yeah. Oh, that is, that means evaluate.
Evaluate.
Yes, sir. Yeah, yeah. So this is the integrated form, and then we're going to evaluate it, these, and subtract. Good question. Good to know that. Any other questions?
I'm confused.
why we have that there.
Why we have which, I'm sorry,
In the first term, why we have that evaluated at.
why we have evaluated at?
Yeah.
So, well, because we have a definite integral, Daniel. So if I had this, then I would just kind of merrily go along, and get it all out. And I'm gonna get a formula, but I still have to do this evaluation. So think about how you would do a normal evaluation, right? You would take your antiderivative, and then you would evaluate. So I still have to evaluate it at the endpoints. And so when you do parts, kind of the like protocol, I guess, if you did this from A to B, as you do that part, you evaluate it right at the start, and then, I don't know if that helps.
Yeah.
Is that, okay, cool, good. Why did I? Yes, I will talk about that, absolutely. We'll get there. Let's get this little chunk here first. So, but you're cool with that, you're cool with that, right? You're just curious why I did that, yes. Good, that's good. What the hell does this do? Well, this thing here, let's rewrite it just a little bit. This is actually negative. We're going to assume S is positive. We're going to have to. You'll see why in a second. This is actually negative 1 over S t, or the t goes on top, e to the st. And we're doing that from 0 to infinity. If S is positive, this is an exponential function. And let's just look at this really quick. It's limit as t goes to infinity of t over e to the st. How do I do that limit? L'Hopital, top's going to infinity, bottom's going to infinity. So this is a L'Hopital's problem. And plugging in the infinity is doing a limit, and that limit involves a L'Hopital. So this is limit as t goes to infinity, derivative of the top over the derivative of the bottom. Since S is positive, this is blowing up. So this whole thing is dying to 0. So at infinity, this dies, is what I'm trying to say. What happens when I plug in the 0? What happens when you put 0 into this expression? What do you get? 0, right? When you let t equal 0, you got a 0 right here. So check this out. Think of it this way. The infinity, e to the negative infinity, think of that as 0. It's 1 over e to the infinity. That's a small ass number, that's 0. And then when you put in the 0, that kills off this. Lots of L'Hopitalable things need to happen here, but what I'm trying to convince you in so much is to believe that this whole thing dies and goes to 0. I mean, you'll be happy if it does, right? Like, certainly we would be happy to not lug that shit around. But it mathematically does, provided this is true. So all I'm left with is, oh wait, oh no, there is one part. There is, no, we're good. Sorry, let's go to 0. Sorry, I'm thinking of something else. So this turned into 1 over s integral 0 to infinity e to the negative st times 1 dt. Why did I write it like that? What does it look like that we've seen? Does it not look like the integral we did on the right side of the board? This is the Laplace transform of 1. So this turns into be 1 over s Laplace transform of 1. I know what the Laplace transform of 1 is. It's 1 over s. And we're assuming s is greater than 0. This thing out in front is going to happen a lot. And we're going to do one more, and then I think you're going to be pretty happy with what we see. You don't seem happy or sad right now, and that's good. I'll take that. The not sad part is important. So Vivian, did that actually help? Why? Okay, cool. I was just looking for a rhythm there. Let's do one more. And let's do something a little bit more wild. Let's take the Laplace transform of t to the nth power. So that's going to be integral 0 to infinity, e to the negative st, t to the n dt. I'm going to do parts. So I'm going to do parts again on this. I'm going to let u equal t to the n. I'm going to let dv dv be e to the negative st. And then du is nt to the n minus 1. And v is negative 1 over s e to the negative st. And this turns into then, using those parts, u times v from 0 to infinity minus integral v to u. Look, it's a little different now. So this becomes plus 1 over n over s, actually, because this n is a constant, this s is a constant, or this 1 over s is a constant. That all comes out in front. Integral 0 to infinity, Laplace, oops, I'm giving away my story. E to the negative st, t to the n minus 1 dt. Let me stop. I know I'm going fast. This whole thing goes to 0 for exactly the same reasons as that one does. The negative infinity makes the e to the negative st so heavy that it kills off any power of t to the n. And when you put in 0, you just get a 0 here. So the infinity kills this, the 0 kills this, it dies at both ends. All I'm left with is this. So the Laplace transform of t to the n is equal to n over s, Laplace transform of what? T to the n minus 1. Aha, now we got a recursive relationship. We peel this down, right? We peel this sucker down. Let's actually get some solid cases in here to help our understanding. We know when n equals 0, we know when n equals 1, what we want to do is like figure out the next one. So the Laplace transform of t squared is going to equal 2 over s Laplace transform of t. And the Laplace transform of t is 1 over s squared. So it's 2 over s cubed altogether. Check that out. So I'm using this fact here, that the Laplace transform of t is 1 over s squared. I'm using this recursive relationship, and I'm getting myself out a formula pretty pronto. Let me ask you this. What is the Laplace transform of t cubed? Can you do that one for yourself? What is Laplace transform of t cubed? And then we're going to generalize, come up with a formula. We don't have to do this every time we've got like a power of t. Six over s to the fourth. Getting there. Let's just make sure everybody's coming along. I'm going to write the top in a really suggestive way. Factorial notation, is that cool with everybody? So, does anybody need me to just talk about factorial notation, or does this seem okay? Cool. So look at that beautiful formula. Now think about what's going to happen if you go to t to the fourth. If you had t to the fourth here, what would happen? Well, you'd get a 4 over s, and then you'd have the t cubed here. And what would that do? It would just tack a 4 over s out in front of this. So the Laplace transform of t to the 4th would be what? What's the Laplace transform of t to the 4th? Look at the rhythms.
4 factorial over s to the 5th.
That's it. There we go. So that's easy. That's beautiful. We don't ever have to pay that price again, so we paid heavily. Yes, sir.
Oh, never mind. I figured it out.
Wow, fantastic. Amazing. That was really quick. Beautiful. So let's put our first Laplace formula up, our transform formula. The Laplace transform of t to the nth power is what goes on top?
T factorial?
N factorial. Yep, yep.
Oh, yeah.
Yes, I knew that's what you meant. Over s to what power? N plus 1. It's 1 more than the power of t. Yes, we'll get there. It's all good. First formula. Beautiful. Cool. Let's do another one. We're going to crank out a few of these today. So let's see if we can find the Laplace transform of e to the k times t. So k is a constant. Can be positive or negative. We've seen that all over in diffie-q, right? Like you don't do a diffie-q without e to some power. That's freaking bread and butter. So we write the definition out, put in the Laplace kernel, e to the kt dt. Ooh, this one's looking really nice, huh? Let's go through it together because we just have to be careful. I would combine those e's. So it's actually e to the k minus s t dt. Does that sound okay? Check that out using the exponent laws. Are you believing that, Nathan? Okay, I just wasn't sure. I got the bad glasses on, that's why I can't tell. Uh-oh. Oh, I got them this time. I know where they're at. I couldn't tell which Nathan was agreeing with me. There we go. Much better. Feel free to do this. I'm going to do it slowly and quietly. Feel free to knock this out. Yeah, I don't want to do anything. I'm going to let you try for a minute. Oh, here's my lid. Nice. You're probably going to want to assume s is bigger than k at some point, so that's a negative exponent. I'm curious. I'd love to see somebody knock the Guinness. What's good math going on? Oh, you're fine, James. I just couldn't make out that word. I was like, I don't know. That S is bigger than K. Yes, exactly. Yeah, exactly. Yeah, you got something? Maybe. I take it. Thank you. You told me. Beauty. Yes? Yeah. Fantastic. So you definitely need to assume S is bigger than K, because if that's a positive exponent and you put in infinity for T, it blows up. Let's see here. Oh, this is the abuse of the notation is becoming worse by the second. That's funny. I'm glad there's no like math profs in the room. At least not the ones I work with. I feel like they'd give me shit about it. What does this do if if this is a negative thing, and we've got, what is e to the negative infinity? 0. So this dies. What is this? Goes to 1, because it's just e to the 0. So the answer is negative 1 over k minus s. But boy, that's terrible to have that negative there. So let's change it to 1 over s minus k and be happy and leave it be. And we're going to say that s has to be bigger than k. So there's our next transform. I'll give you an example. Let's write the rules up here. So next rule, Laplace transform e to the kt is 1 over s minus k. And you should keep these little conditions by the side. S greater than k. So just really quick, let's use what we have to do something a little more sophisticated along with the linearity. If I asked you to find Laplace transform of 2 minus 3t to the 5th plus e to the negative 4t. Linearity says I can break it apart, pull scalars out in front. So you won't do this every time, but boy, let's just do it once. Breaking it down, going back to the fundamental transforms. I'll let you finish it up. I kind of want to hear what you say that last one is.
Is that 3 times 5 factorial? Or
Yes,
15?
yes.
Okay.
Yes. So this would be like 360 if you worked it all out. Yes. Sound good? Everybody cool with that 1 over s plus 4 because the e's got a negative k on it, so it's a little bit of a trick, or kind of trick, just not much, just a subtlety that I wanted to at least catch there. Oh man, we are so close to being able to solve a differential equation. We've got one more thing we're going to do. So I'm going to tell you, here's the game. I'm going to tell you the game over and over again so that when it comes, you'll be like so ready for it. The game is going to be this. We're going to take some differential equation like, let me see, what do I got? I got one here that we're going to do, provided everything goes well today. So let's just say I had y double prime plus 4y prime plus 3y equals t minus sine of t. And maybe don't even write this down actually, maybe just kind of like listen to what I'm saying because you'll see this many times. y prime of 0 equals something, and y of 0 equals something. Here's the game we're gonna play. We're going to take that equation, we're going to apply the Laplace transform to both sides. This side, we can almost do, we don't know what sine turns into, but I'm gonna tell you in just a minute. So we take the Laplace transform of this, we take the Laplace transform of this. The cool part is gonna be the Laplace transform of this side incorporates the initial conditions when you take the transform. We're gonna get the Laplace transform of all this stuff. We're going to solve for the Laplace transform of y. And we're gonna get some function in S over here. So we're gonna solve for this, and then we're gonna undo it using those formulas backwards, and we'll have our solution. That's the game. Take your equation, go to Laplace space, do some algebra, come across with the algebra, come back down, solved. Yes, ma'am.
What is that symbol?
This symbol here?
Yeah.
That's just a capital Y, sorry.
Cool, okay.
That's a fancy Y. That's, you'll be getting used to that one too. That's my Laplace transform of Y symbol. Good question, Kitra. So let's get a few more out here. The Laplace transform, I'm not gonna prove these because they're just, you can read a proof anywhere online. And you don't wanna see it either. I'll give you some easy ways to remember these two. So the Laplace transform of sine has the k on top, and then it's got s squared plus k squared on the bottom, and we assume s is positive. The Laplace transform cosine of the kt has the s on top, and then s squared plus k squared in the bottom, s is positive. These two seem completely backwards, and that's how I remember it. The sine doesn't have the s on top, the cosine has the s on top. The sine has the k on top. Pretty easy once you think of that. It's just backwards from what it would seem like it would be. So now we got those. Pretty easy. So now the real stuff. How do I take the transform of this side here? So let's build it up. There's a couple other things, like how would I do t times e to the 3t? We're not going to get to that today. We'll get to that on Monday. Combos of these functions, Monday. But today we're going to have enough to get this rocked out. So let's talk about now Laplace transforms of derivatives. All right, we're gonna do this like we've done everything else here. Little bits, build our way up to kind of an inductive case, right? So we're doing induction, right? Starting off small, seeing what the rhythm is, and then I guess we're not proving things by induction, but induction is hiding out, watching us, wishing we would use it, pretty much. So Laplace transform of derivatives. Let's say I've got this function, f prime of t, and I want to take its derivative. There's something I'm not saying, and I'm deliberately not saying it. It's like, when is it okay to do this stuff? And there are certain things that you can take the Laplace transform of, and others you can't. Everything we will need to do is going to be okay. On Monday, I'll talk about the subtleties. I just want to get this shit going today so that you can be, have something to do over the weekend with your friends. So this is going to be integral 0 to infinity, e to the negative st, f prime of t, dt. Okay. If I wanted to work my way to relating this to the Laplace transform of f of t, any suggestions on a mathematical technique I could use? How can I somehow take this integral and rewrite it as an integral that involves f and not the derivative of f? Integrate, when you say that, say,
Integrate.
that's okay, yes, yeah.
Other way around.
Yeah, so we kind of like want to integrate this up, right? It's not up here anymore, but integration by parts is kind of like the trick here. So I'm gonna let dv be this and let u be this. So again, parts. Parts helps you change things that are derivatives in integrals to higher levels, and vice versa. You can do all sorts of stuff like that. So we're gonna let u equal e to the negative st. Very different from the last time when I was letting u be t to the n. And dv is f prime of t dt. And then du is going to be negative s e to the negative st dt. And v is just f of t. It's the this is antiderivative, so just take off a level of differentiation. Does that sound okay? All right, good. So then, come back, and we use our parts. So I'm going to take u times v. I'm going to evaluate that from 0 to infinity. Something a little different is going to happen here. And then I'm going to have minus integral v to u. Well, notice there's already a minus s, so that becomes a plus s. And then I have integral 0 to infinity e to the negative st f of t dt. So check that out. Make sure that you see what's going on. And let's look at this piece. Do you see that this is actually the Laplace transform of f of t? Yeah, right. So I worked it into there. Kitra is convincing herself. Are you convinced yet, or yeah?
I'm okay.
Okay. I'll lay off. Back off. We can talk about this in a minute. Let's look at this piece here. So I'm going to abuse notation again. It's e to the negative s times infinity. I feel like a real asshole writing that, but I'm doing it anyway. And then minus, now I put in the 0, and I get e to the 0, 1, minus f of 0. So notice the 0 makes this very different than the last thing we had. It doesn't kill it off. And then plus s times the Laplace transform of the f of t function. This piece here, because it's e to the negative infinity, we're going to assume s is 0 again, or s is positive at least. We're assuming that the function f is such that this limit would go to 0. So that wouldn't always happen, but the class of functions we're doing this to, that will always happen. This e will always dominate things at infinity. So we're cool to go as long as we have the right functions. So check it out. I've got my final answer. The Laplace transform of the derivative is equal to negative f at 0 plus s times the Laplace transform of f. So I got rid of the derivative and exchanged it for an s and then a constant. We've got one more to do before we're really pretty much set free to do a lot of things today. Let's do the second derivative so you can see the, let's do something. Yeah, fine, let's do the second derivative. I think it's better maybe if just go a little slower to see the rhythms. So we do Laplace transform of, my pen is dying. Very sad. There's like, the only pens in here are red. There's like 10,000 red pens in here because no one ever wants to use them. And this is all I got. And I'm out of my personal stock. Okay, let's try this. So Laplace transform of f double prime of t equals integral 0 to infinity e to the negative st f double prime of t dt. What do you think I want to do? Ideally, I want to work myself back up to f. I want to work myself up and find the Laplace transform. I want to find e to the negative st f of t in there somehow. What do I do? Integrate, definitely. With what technique? Parts. Yeah, we're going to use parts again. So we're going to let u be e to the negative st. We're going to let dv be f double prime of t. So du is again negative s e to the negative st dt. V is f prime of t. So putting this all together, I'm going to go to red. I'm sorry. I got to. I cannot take that weak pen. That's better. It's better or not. We'll take it. So this is going to be uv from 0 to infinity minus integral v to u, which becomes plus s. Integral 0 to infinity e to the negative st f prime of t dt. Oh yay, I got rid of a level of differentiation. Yeah. And actually, we already cranked this out, right? We literally just did that right over there. So we don't have to do that again. We just got to figure out what's up front here. So the stuff up front, here's again, horrible abuse, observers of this is garbage, but it's only for intuitive understanding. Put in the infinity, put in the 0. Notice when the 0 goes in, it makes the e a 1, and then I just get f prime of 0. And then plus s times the Laplace transform of f prime of t. Let's clean this all up. Again, not shockingly, this part dies. And we're left with the Laplace transform of f double prime of t is equal to negative f prime at 0 plus s times the Laplace transform of f prime of t, but we got a formula for that. This is cool because this should be a prime here. You can't see it. Let's undo it completely. So let's see, so that's negative f prime at 0 plus s times, and what was this? Well, it was negative f at 0 plus s times the Laplace transform of f itself. And I'm going to simplify. So this is negative f prime at 0 minus s f of 0. Derivative, no derivative, plus s squared Laplace transform of f of t. That is how you do the second derivative. Are you starting to see a rhythm? There's a little bit of a rhythm rolling here, all right? We're getting this power in front of the Laplace transform matches the level of the derivative, right? This was for the second derivative. I got an s squared out in front. I've also got the lower order derivative. So if I'm doing the second derivative, here I see the first derivative and then the original function just evaluated at 0. Let's see if we can extrapolate, make a big leap now. So, from that, I can actually get all the formulas I need. If I wanted the formula for now triple prime, I could just say, that's the second derivative of the first derivative, and I could replace every f here with f prime, and then I'd get down there Laplace transform of f. Here, let me show you what I mean. So I'm just saying it. So let's say I wanted triple prime. I go, oh, okay, well that's the Laplace transform of f prime, second derivative. And that's equal to, so now this is the f right here. This is the thing that's going inside there. So it's going to be negative f prime of t prime evaluated at 0. That's this, minus s times f prime of t, no derivative, evaluated at 0, plus s squared Laplace transform of the function f prime of t. And then if I simplify this, this is just negative f double prime at 0 minus s f prime at 0 plus s squared times the Laplace transform of f prime, but that was what? F at negative f at 0 plus s Laplace transform of f. And when I make this whole pretty formula out, it's negative f double prime at 0 minus s f at, oh, this should be f prime, excuse me, f prime at 0. And then minus s squared f at 0 plus s cubed Laplace transform of f of t. Are you starting to see the rhythm? That's mostly what, there is a nice rhythm here. So let's see if we can just guess the rhythm without going through all that bullshit. So Laplace transform of the fourth derivative of t, of f, of t. Look at the rhythms. First off, we know there's going to be a plus s to the fourth Laplace transform of f down here. That's going to be in there because that power of that s always matches the level of derivative. And then look at it in front. First you have this thing and then you start adding s's. This is the next level of derivative from the one you're actually working from. So since this is a fourth derivative, the thing out front is going to be a third derivative at 0. And then minus s times f, the second derivative at 0, minus s squared f prime at 0, minus s cubed f of 0, and then plus s to the fourth Laplace transform of f. We don't probably need to go much further than that for a long while. But we can actually solve an equation today. That's pretty cool. It's gonna be good. You're gonna like this. It's freaking amazing. You pay a lot up front, a lot of overhead here. Check out the rhythm. Notice how the exponent on the s and the level of differentiation out in front always adds up to 1 less than the level of the derivative. So like here, that was third derivative, second derivative, first power, first derivative, so that adds up to 2. Then this is 2 here. So I don't know. Maybe I shouldn't even be bothering. Do you see the rhythms? That's not too bad, right? It's a little complex. All right, let's solve the problem. So now we know how to do derivatives, and now you can see how they incorporate initial conditions, right? That's actually asking me, what is f at 0? What is f prime at 0? So let's do one problem, call it a day. Solve. What was the one I had up here? It was y double prime plus 4y prime plus 3y equals t minus, no, let's go simpler. Sorry, that's a little too crazy. That's too freaking crazy. Here's a better one. Solve this. Y prime minus 3y equals t. That's better. And let's just say y at 0 equals 1. Let's start off chill. Let's get too excited. Plenty of time for excitement next week. Okay, so step 1, put some nomenclature in here. So we're going to let capital Y equal the Laplace transform of our solution. And then I'm going to take the Laplace transform of that equation on both sides. So here we're going to take L. Now let's write it out. So it's Laplace transform of y prime minus 3 because of linearity, Laplace transform of y equals the Laplace transform of t. Laplace transform of t is going to be 1 over s squared. Let me stop so you follow. This part really is important to follow. Yes, Hans?
Sorry, can you re-explain why on the right side of the equation t moves to 1 over s squared?
Yes, so I'm taking the Laplace transform on both sides. So when I take it on this side, it looks like this. On the right side, I did this, and I maybe should have written this like this first. But the Laplace transform of t, now I'm using that upper left-hand formula with n equals 1. So it's 1 factorial over s squared, using this formula. Does that make sense?
Mhm.
Awesome. Other questions? I really am excited to show you because I think you're going to be astounded. So now, Laplace transform of y prime, that is going to be, let's put the formula up here. So Laplace transform of a derivative was equal to negative the function evaluated at 0 plus s times the Laplace transform of that function. This is our formula. So I'm just going to use that over here, except we have y instead of f. So this thing becomes negative y at 0 plus s times capital Y, which is the Laplace transform of y. So you could call that capital F if you wanted. But this is just, again, the Laplace transform of y in shorthand. And then I have minus 3 capital Y's because that's just the Laplace transform of y right there. They didn't need to do anything except relabel it as y. And then on the right, I got 1 over s squared. Y at 0 is 1, so I'm going to use my initial condition and replace y at 0 with 1. So this is equal to 1 init condition. And so what we've got now is negative 1 plus s minus 3 in quantity times y. Notice I can have a y in common to both of those. I'm just going to factor it out. Equals 1 over s squared. Get everything to the right side that doesn't involve y. So the goal now is to solve for that capital Y. So what we get is capital Y equals 1 over s squared plus, wait, let's leave this s minus 3 out front for a second, plus 1. And then I divide by the s minus 3. So this turns into y equals 1 over s squared times s minus 3 plus 1 over s minus 3. Now I hope to Christ I did the partial fractions, right? And I did. Good. So your new friend is going to become partial fractions expansions. Yeah, you can see it right there. So now, check it out. Who's this the transform of? E to the 3t. That is the transform of e to the 3t. So now the plan is undo this. Take the inverse transform, and that just means going backwards. And today it's easy. We're going to have to learn some tricks to do this in general. But let's get this up here. Let me just summarize really quick. So y, the Laplace transform of our solution is this, and I did the work for us. This we can undo. We know that comes from e to the 3t. This looks really freaking complicated. So after a par frac, a free one that I've done for us, we'll talk about that again, so don't stress if that you're not familiar with that. This turns into negative 1/9 over s plus negative 1/3 over s squared plus 10/9 over s minus 3. That's this piece. And then we still have the plus 1 over s minus 3. Oh, wait. Yeah. Oh, shit. No, that is 1/9. Excuse me. Yeah, I did something, I combined them. That's actually 1/9 here, sorry. It combines to a 10/9. Okay, let's actually bring these together, because these are the same thing. So this is equal to -1/9 over s plus -1/3 over s squared plus 10/9 over s minus 3. Oh my God, we're done. We are done. Let me refresh your memory on a couple of things. The Laplace transform of 1 is 1 over s. So any multiple of 1 over s is a constant. So in other words, L inverse of 1 over s is 1. That's another way to say that. What does this turn into? What is this the transform of? -1/9, perfect. Beautiful. And then this one here, we know that the Laplace transform of 1 over s squared, excuse me, of t is 1 over s squared. There's a 1 over s squared, but it's got a -1/3 in the front. What goes here? Where does that go? So here, let me write an inverse transform of 1 over s squared is t. So what's the inverse transform of -1/3 over s squared? Thank you, -1/3 t. What is that the transform of? 10/9, what? E to the 3t. Yeah? We're done, we solved it. Pretty cool. The partial fractions takes the role of, like, I don't know what, everything else we've ever done. We're done. Look, no solving for C, no systems of equations. Pretty good. This is what we'll start doing next week. So, yay! Let's call it a day. I'll hang out and talk to anybody who needs to talk about anything. Time to go to work?
Well, yeah,
Oh,
I'll start my work.
oh geez. Oh geez. What's happening? Not me. I'm not involved.
No.
Okay, good.
I just want my skills checks mixed up because we just took 4 last week.
Skills
And I
checks?
just did 3
What class?
all logical proof and combinatorics.
Oh, you guys do a lot of work in those, don't you? It sounds exhausting. Is that Dr. Patnott?
Yeah.
I would totally fail Dr. Patnott's class. Because she would need me to work harder than I can work, I think.
It's just so impressive.